Hello and a very good morning to my fellow panels. My name is Somashana and I'm from Politeknik Seberang Perai. Today the topic of my presentation is optimizing indigo extraction methods for sustainable dyeing. This presentation explores the development of environmentally friendly and sustainable methods for extracting indigo dye from the Indigofera Tinctoria plant. The focus lies on optimizing extraction techniques, including fermentation, enzymatic processes, and green chemistry principles to improve yield, purity, and consistency. I will present about the introduction. Indigofera, a plant genus known for producing indigo dye, has a rich history and cultural significance in textile traditions worldwide. Extracted from the leaves of the Indigofera tinctoria plant, the dye is prized for its deep lasting color and environmentally friendly properties. The genus Indigofera, particularly Indigofera tinctoria, has been a cornerstone in the history of natural dyes, renowned for producing the iconic indigo dye. Indigo dye extraction, especially from I. tinctoria, is rooted in ancient civilizations such as India, Egypt, and China, where it was traditionally used for textiles before it spread to other parts of the world, including Indonesia and Europe. Unlike synthetic dyes, natural indigo has minimal ecological impact as it is derived from renewable plant resources and does not involve toxic chemicals. Today, as consumers seek sustainable alternatives, Indigofera stands out as natural, eco-conscious choice that meets both aesthetic and ethical demands. Natural indigo dye production involves extracting indigotin, the compound responsible for its deep blue hull, through sustainable agricultural practices. Unlike synthetic dyes, which often contain harmful chemicals, natural indigo is derived from renewable plant resources, making it an environmentally friendly option. Next, I will present about challenges and opportunities. Inconsistent quality. The natural indigo industry faces challenges such as inconsistent product quality, low yield, and limited scalability due to reliance on artisanal methods. Advancements in extraction. Advancements in extraction techniques and cultivation strategies have paved the way for enhancing the efficiency and consistency of natural dye production, further solidifying its role in sustainable industries. There are a few advancements in indigo extraction methods, which is ultrasound-assisted extraction. UAE employs ultrasonic energy to enhance the diffusion of plant-derived processes, leading to improved yields and reduced extraction times. This method aligns with green chemistry principles as it minimizes solvent use and energy consumption. There is also enzymatic hydrolysis method. Another promising technique involves the application of microbial enzymes. For instance, engineered bacteria capable of producing indigotin directly from glucose have been investigated to overcome the challenges of inconsistent yields and high labor costs in traditional methods. Lastly, continuous solvent extraction. Continuous solvent extraction methods have also shown potential for industrial scalability. By combining calcium hydroxide in controlled air bubbling, this technique facilitates the separation of indigotin and indirubin, resulting in higher quality natural indigo. Next, I will talk about applications in the textile industry. Wad dyeing. Traditional dyeing techniques such as wad dyeing involve reducing indigo into a soluble form for application. Upon oxidation, the dye reverts to insoluble state, imparting vibrant and durable colors. Sustainable fashion. In modern applications, natural indigo is increasingly used in sustainable fashion. Artisanal techniques, especially in regions like India and Indonesia, have gained global attention for their eco-conscious practices and cultural preservation. Lastly, biotechnical advancements. To address challenges like high production costs and competition from synthetic dyes, hybrid approaches combining traditional methods with biotechnological advancements have been explored. Next, I will present about color fastness testing in natural indigo dye textiles. Wash fastness. Wash fastness is an essential performance indicator for dye textiles, determining the resistance of fabrics to color fading or transfer during laundering. For natural indigo dye, enhancing wash fastness remains a challenge due to its weak molecular interaction with textile fibers. Second, light fastness method. Light fastness measures fading under light exposure. An 8-point scale is used where 1 is very poor and 8 is excellent. Then, rubbing fastness. Rubbing fastness evaluates transfer of color during friction, dry and wet rubbing. Lastly, perspiration fastness. Perspiration fastness assesses dye stability against acidic or alkaline perspiration. Next, I will present about color fastness rating framework. The results of color fastness tests are often expressed using a scale that ranges from 1 to 5, with 1 indicating poor fastness and 5 indicating excellent fastness. The table below shows color rating scale and standard. First test type is wash fastness, where it uses a scale from 1 to 5, which indicates resistance to color loss during washing. Higher ratings signify minimal fading. Next, light fastness. It uses a scale from 1 to 8. It measures fading under light exposure. An 8-point scale is used, where 1 is very poor and 8 is excellent. Next, rubbing fastness. It uses a scale of from 1 to 5, which evaluates transfer of color during friction, dry and wet rubbing. Lastly, perspiration fastness. It also uses a scale from 1 to 5, which assesses dye stability against acidic or alkaline perspiration. Now, I will look into the methodology on how to extract indigo from Indigofera tinctoria. Firstly, fermentation process. Fresh leaves are first collected, cleaned, and soaked in room temperature water within a sealed container for 24 hours to initiate natural fermentation. Then, a calcium hydroxide solution is prepared and added to the extract to adjust the pH to approximately 9, facilitating the formation of indigotin, the blue pigment. Then, aeration and sedimentation process. The solution is aerated vigorously using electric whisk for 10 to 15 minutes, promoting pigment precipitation through oxidation. The mixture is left to settle for 3 days, during which the indigo pigment collects at the bottom of the sediment. Then, drying and powdering process. The concentrate pigment is then dried in a well-ventilated area, forming a solid that can be grounded into powder. The fabric dyeing process includes 3 steps, which is dye wet preparation, fabric preparation, and dyeing and oxidation. An indigo dye wad is prepared using the extracted indigo pigment, a reducing agent, and an alkaline solution. This creates an oxygen-free environment where the indigo turns into a soluble form. The fabric is then prepped by washing and soaking it in water before being submerged in the dye wad. The fabric is dipped and oxidized multiple times to achieve a deep blue color. Each time the fabric is lifted from the wad, it appears green, but it turns blue as it interacts with air, creating that signature indigo shade. Now, I will look into the dye experiment setup. To evaluate the effectiveness of indigo dyeing under varying conditions, 3 sets of experiments were conducted using 100% pure cotton fabric as a substrate. Each experiment tested a different dye concentration, which has 2 grams per liter, 4 grams per liter, and 6 grams per liter, while maintaining consistent conditions for temperature, pH, and fabric material to ensure comparability. The dyeing temperature was held at a constant 60 degrees Celsius, a level optimized for indigo absorption, and the pH was adjusted to 9, the ideal condition for stable dyeing. The dyeing temps were set at 30, 45, and 60 minutes for the respective experiments to assess the time dependency of color adherence. Observational parameters included color uniformity, depth of color, shade variation, wash fastness, and also rubbing fastness. Next, I will present about results of the wash fastness evaluation. The performance of natural indigo dye on cotton fabric was assessed using the grayscale color rating system, focusing on wash fastness across 3 types of dye concentration, which has 2 grams per liter, 4 grams per liter, and 6 grams per liter. The grayscale color rating, based on ISO 105/606 standards, evaluates the resistance of dyed fabrics to color fading, with high ratings indicating superior durability. For the 2 gram per liter concentration, the fabric achieved a grayscale rating of 3, reflecting moderate wash fastness. This result indicates incomplete dye fixation at lower concentrations, leaving residual dye prone to removal during laundering. Next, at 4 gram per liter, the fabric showed an improved grayscale rating of 3/4, highlighting more robust dye absorption and fixation due to the increased availability of dye molecules. Lastly, at 6 gram per liter concentration, did not demonstrate any further improvement with a rating of 4. This plateau suggests that higher dye concentrations exceed the fabric saturation threshold, resulting in diminishing returns for wash fastness. To further enhance the application of natural indigo dye, several areas for future research and development are recommended. First, optimizing key parameters such as pH, temperature, and modern type can significantly improve dye fixation and fastness properties, making the dyeing process more efficient and reliable. Exploring eco-friendly reducing agents derived from natural sources such as date palm or banana extracts could provide sustainable alternatives to conventional chemical processes, reducing environmental harm while also maintaining high dye performance. Lastly, the study successfully demonstrated the potential of natural indigo dye as a sustainable alternative to synthetic dyes, focusing on its application to cotton fabrics and evaluating its wash fastness properties. These results reveal that a dye concentration of 4 grams per liter achieves optimal wash fastness with a grayscale rating of 3/4, highlighting its effectiveness in color retention during laundering process. High concentrations such as 6 grams per liter showed no additional benefits, suggesting a saturation point in dye fixation. These findings underscore the importance of balancing resource efficiency with performance in natural dyeing processes. Moreover, the incorporation of eco-friendly techniques such as natural reducing agents further enhance the environmental sustainability of indigo dye production.